satisfy a first-order model. That's it.
All right, so thanks a lot for inviting me. I'll talk about first-order model counting and how you can use it to compute probabilities in an interesting way. So first, I want to give a very high-level motivation. It's very similar to what other people talked about today. But what is this stuff good for? So here's one motivation. What I would like to do is I would like to ask Google, does there exist a co-author of Einstein and Erdős? And currently, the systems that we have don't really allow us to answer these questions. But if you look at the small print, you see, for instance, that Einstein has an Erdős number of 2, which means that, yes, there should be someone in between. So this is a motivation to have query answering. And actually, all the ingredients are already there. So Google knows about Albert Einstein. It has in its knowledge graph all of this information. It also knows about Erdős. And it also knows about this guy, Ernst Strauss, who happens to be a co-author of both Einstein and Erdős.
I took a course in complex variance from Strauss.
Ah, see?
UCLA, 1975.
Oh, UCLA, that's nice. Oh, yeah. So clearly all of the entities are in there. We just have to join them and find the right answer, right? So what I would like 10 years from now is that I get this answer. Yes, Ernst Strauss is probably the guy you're looking for. Barack Obama also published the paper. Justin Bieber, probably not, right? So why is this uncertain? Well, all of these facts come from information extraction systems that are statistical systems. So really, we need probability here. And also, for the machine learners, this cannot come from labeled data. You will never have websites that list specifically who are, co-authors with one author in between. I mean, some of these things you really need query evaluation. So, okay, I'm preaching to the choir here, but this is my motivation for probabilistic query evaluation. So that's one motivation. And the reason, by the way, that it's not solved yet is because the likes of Google and Apple and Amazon, they're solving a much more simple problem, which is answer queries that explicitly appear on some website. For instance, in January, if you would ask who's playing in the Super Bowl next week, you would get last year's teams. So this is an article in the New York Times that tells you, actually these systems, they're really not there yet. So they definitely don't care about doing joins on their probabilistic databases yet. So that's one motivation. Here's a completely different motivation, very similar to what Lisa Gatour talked about, is statistical relational learning. We want to have things like Bayesian networks, but we want to extend it with relationships. For instance, saying that friends have similar smoking habits and that asthma can be hereditary. And then there's a whole bunch of different representations out there, including PSL, including Broeck. They all have their advantages. But it looks roughly like this. You have a relational model with probabilities or weights. So that's my second motivation, and I'll get back to these both of these motivations later on after I explain the more technical stuff. So why do we need first-order probabilistic reasoning? Why do we need to have a special algorithm to do probabilistic reasoning for these relational representations? And here's a very simple example that shows you why we need this. And it's actually a system. So someone tried to use one of my probabilistic inference systems to solve this problem here. You have a deck of cards that's shuffled, and you would like to ask, what's the probability that the first card is hearts? Really easy, 1/4, right? What's the probability that the last card is spades, given that the first card is the queen of hearts? A little bit more difficult, conditional probability, 13/51. So these are really simple questions that you would like to maybe ask when you're doing some kind of game engine development. So let's try to automate this. Let's try to build a probabilistic graphical model to answer these types of queries. So here you have a random variable for every card in your deck, and the values tell you which card is behind this position, right? And then let's take our favorite probabilistic inference algorithm to answer these queries, right? And some of you may know what's going to happen next. So what you get is a fully connected graphical model, because all of these random variables, they say that, for instance, this card and this card, they cannot have the same value. And for every pair, you have this type of constraint between your random variables. And if you run your textbook AI probabilistic reasoning algorithm on this, no matter what you choose, you get something that will build you a table of 52 to the 52 rows. So even though this is a super easy problem, actually we don't really have general purpose tools that can solve these types of things, I would argue. Okay. And it's not just in this kind of contrived example that you see this behavior. If you take your statistical relational model For instance, a very simple one that says faculty web pages are more likely to link to course web pages. And even if you have just 26 web pages, you already have this graphical model here. And as you can see, it's also very densely connected and very symmetric, right? If you only have 1,000 pages, you already have 1 million random variables and factors, and you couldn't even draw this on a slide. So traditionally, we would say using algorithms like variable elimination, this would be highly, highly intractable, but we'll try to deal with that with the algorithms that we develop. Okay, so what's going on here? Why is this an easy problem for us and not for these general purpose algorithms? Well, the reason is that if I ask this query for the first card, being the Queen of Hearts, or the Queen of Hearts, or for the second or the third one, I always get the same probability, right? So what you really have here is some additional property, which you could call some high-level reasoning. You don't reason about every card individually, you reason about them as a whole group. There's relational structure because you can say that there are entities and relationships between them, and this is how you see the world when you solve this problem. You could say they're symmetric, the cards, or you could say in statistics that they're exchangeable, right? And in lifted inference, what we try to do is build inference algorithms that take into account these properties to speed things up. So how does it work? How do these algorithms actually exploit these symmetries? So to explain this, I will also use this very basic problem of model counting, which I think some people already mentioned. So in model counting, you're trying to count solutions to a sentence in propositional logic. In first order model counting, you assume that there is some finite domain in a sentence in first order logic, and you try to count how many solutions are there to my sentence in first order logic. And if you, for instance, have this sentence saying on every day, if it's rainy, then it's cloudy, and there's only one day, then these are all of your possible joint assignments to your variables, and 3 of them are models, right? It's pretty easy. But now I can also increase the domain. I can say there are 2 days, then I have this many joint assignments, and now there are 9 models. Right? And what we'll end up using to as a basic engine for probabilistic reasoning in this context is something called weighted first order model counting, where the weights are now the difference. And here we say that there's a weight for every assignment you could make. If you say that it's rainy on a Monday, it's weight 1. If it's not rainy on a Monday, that gets weight 2. And for every possible assignment you make, there's some weight or some cost associated. And now for every model, you can also just multiply these costs, sum them up, and you get your weighted first order model count. So weighted model counting, which is the same thing for propositional logic, is kind of like a basic engine for probabilistic reasoning in Bayesian networks, in many propositional representations. And now it will turn out that we can also solve a lot of relational probabilistic reasoning problems using this task of weighted first order model counting. So how do we build engines that do this? Well, it's actually really easy. It's almost the same algorithm that Dan Suchu introduced this morning. This is what he introduced. You have some rules. The probability of the negation of a query is 1 minus the probability of your query. If you have independent queries, you can multiply their probabilities, and so on and so on. Right? So remember these from this morning. Well, if you want to do weighted first order model counting, the rules look almost exactly the same. Only there are certain things called these normalization constants. So think of just model counting. Assume that every model has weight 1. Then this tells you that the number of models of the negation of a sentence is just the number of total interpretations minus the number of models of the negation of that query. Right. So all of these rules, they have their weighted analog. And don't worry too much about the details here, but it's essentially the same algorithm that Dan introduced this morning. Right? And indeed, if you have a general weighted first order model counting problem, this is kind of the best you can do. And everything Dan talked about, the dichotomy, all those things kind of carry over to this problem of first order model counting. But actually in AI, we're interested in a slightly different version of the first order model counting problem. And it's the one that you get when you take things like Markov logic networks and you convert them to this specific problem. So here's an example of a simple Markov logic network. Smokers are more likely to be friends with other smokers. And the way that we reduce this to a model counting problem is by constructing a formula that will count the models of, and then also a weight function that assigns a weight to every possible assignment you make. Right? So this is the formula. It's the same formula we have in the MLN, but now we make this formula equivalent to a new relational symbol. And the only thing that this does is it carries the truth value of your formula in every possible world. Right? So where previously you would say, depending on whether this sentence is true for every x and y, you get this weight. Now you say, depending on whether this sentence is true for every x and y, f of xy would be true or false. It's really capturing that sentence. All right. Okay. People don't look confused usually. Okay. And now it's really easy. Now we just have to define our weight function, and our weight function says every time that f is true, we will multiply by this number here, e to the 3.75. If f is false, then we multiply by 1. And if you know a little bit the semantics of MLNs, that's exactly what is the definition of this weight here. It says that every world, for every pair of people for which this sentence is true, you multiply by e to the 3.75 to get the weight of your world. And then later you have to normalize. And indeed, this normalization, this partition function of my Markov logic network, which is the partition function of the Markov network I get when I ground it to a propositional Markov network, this is the same as the weighted first order model count of this sentence with respect to this weight function here. Right, so that's why we say that all of these complex correlations that you get in statistical relational learning, you can just turn them into a query on a probabilistic database, or equivalently a first order model counting problem on a sentence and the weight function. Right? That's how all of these things are connected. All right. And now with this extra assumption that we have this type of reduction going on, there's one key observation, which is that all of these weights of all of these tuples, they're all exactly the same. Right? For every pair of people, if the sentence is true, you always multiply by the same number here. So these tables are completely symmetric. And instead of assigning a weight to a tuple, what you're actually doing here is assigning a weight to a relational symbol. And this allows us to actually come up with additional inference rules beyond the ones that Dan uses that will allow us to speed things up. So these are the rules. Here's just an example. Previously, if we had this variable, for all z, the sentence has to be true, we will multiply, if they're independent, multiply these probabilities for all of these instantiations of the sentence. Instead of multiplying things n times, now we can just take it to the power of n. Now this is a bit abstract. Let me just give you an example of a very specific way that we use this property of symmetry between the weights to compute probabilities or model counts. So let's assume that all of the weights are 1. They're all symmetric and they're all 1. So what we're now doing is just counting how many solutions are there, and the weights, they're kind of redundant now. So how many solutions are there to this sentence in first order logic? For all people x and y, if x smokes and x is friends with y, then y has to smoke. I don't know if this is immediately obvious how many solutions there are. So I'll tell you, but first observe that this is actually a hard query, right? We cannot compute this with, if we don't, so on a probabilistic database, this would be hard to compute. So how do we compute it if we just assume that all of the weights are 1, all of the weights are symmetric? Well, if I tell you precisely who smokes, I give you a database of all of the smokers, and I tell you that k of them smoke, then it's pretty easy. Then you can just count how many combinations are possible for the friendship relation. So if there are k smokers, they can be friends with all of the other k smokers. This is allowed, right? The non-smokers are also allowed to be friends with the non-smokers. The only thing that's not allowed is for the smokers to be friends with the non-smokers. And then this relation is also allowed. So this tells us that the number of solutions that are available after I know all of this information is 2 to the number of friendship relations, except for the ones that have to be false. Right. I didn't tell you, in the beginning precisely who smokes and that there are k smokers. So let's bring it closer to the original problem. Let's say that we know that there are k smokers. So now I don't give you a database, but you know that the number of different databases in which k people smoke is n choose k, right? And then finally, you also know that k, the number of smokers, could be anything from 0 to n. So in total, my model count is this number here. So this is one example of a lifted inference rule that can solve these types of problems and that goes beyond what is possible in probabilistic databases. Why? Because of the symmetries in the problem. Does that make sense? So what should we do if we get such a problem like this deck of cards here? We should just encode it in first order logic. We should say for all positions in the deck there exists one card. For all cards there exists one position, and in the same position there cannot be two different cards. And this completely specifies a deck of cards in first order logic. And then if you run these algorithms, so the algorithm that Dan Suchu developed plus these special rules to deal with the symmetric weights, then you would count the models as being this expression here, and you see that it has these exponentiations, these binomial coefficients that we had in the example before. And if you simplify this, what you get is n factorial, which you know is the number of models of this sentence because it's the number of ways to shuffle a deck of cards, right? And what's interesting here is that we can compute this in time polynomial in n. While previously we had this huge densely connected graphical model with 52 to the 52 rows in our tables, now we can just compute this with two nested for loops. Right, so this is where the power of lifted inference comes in for the symmetric case, in addition to everything you saw this morning. Okay, so this is how the algorithms work roughly.
Computed in polynomial time because you did some symbolic algebra.
Yes. So this expression is generated by the inference algorithms.
This expression, but to evaluate it, are you happy with this expression as the number, or are you trying to get an evaluation?
We try to evaluate it, yeah.
Then I don't know. I'm not sure about the polynomial time. You have to actually evaluate it.
Right. So the exponentiation here takes logarithmic time, right? And then you have two nested for loops, so another quadratic term. But yeah, we can look at that in detail afterwards.
What is your conserve motion?
Okay, data complexity again. Fine.
Yeah. So it's data complexity. I will talk about non-data complexity later. Yeah. Okay. So this is how the algorithm works. So when does it work? When do we get a benefit out of this way of doing things? So first, maybe some of you are wondering why not just use a propositional model counter? Why not use some of the tools developed, for instance, by BART? What's the difference here? So I'll ask you, what happens if you generate a grounding, an instantiation, or the lineage of your sentence here? You generate this huge CNF, and you would give it to a model counter. You think it will work? I mean, you already saw that it's a very densely connected high tree width graph, but okay, maybe it's still tractable for these counters. It's possible. Well, it turns out that no, and I'll give you a very quick intuition why. So this is the same problem shown as a bipartite graph. We have all of our cards and all of our positions, and these are all of the random variables expressed by edges. So this random variable here says that card King of Hearts is assigned to the last position in the deck, right? A model here, so one model of the sentence in first order logic is simply a perfect matching in this bipartite graph, right? It's matching every card to every position. Final observation is that if I count models, I'm counting perfect matchings, okay? And then the last interesting observation is that if I set the weights of my propositional variables, of my assignments, to be arbitrary, then I'm allowed to set them to 0. I can say that it's impossible for the King of Hearts to be in position 52, right? And I can encode this any way I want. So then here's the bottom line. By setting my weights, I can encode an arbitrary bipartite graph by just removing edges here by setting their weight to 0. Counting models is counting perfect matchings, and this is sharply complete for bipartite graphs. So what this means is that any weighted model counting solver, any model counter that can handle arbitrary weights or unit clauses will always require exponential time here, assuming,
But you're really comparing two different types of complexity. It's not a correct comparison, because you're comparing combined complexity with data complexity. Now you can make statement about them, but don't say that one is easy and one is hard when you're comparing two different things. Okay, if you want to do this comparison on combined complexity on both sides, and then we'll see meaningful comparisons.
So this is for a fixed query for just this deck of cards,
But
and for
the point is that once you Booleanize it, the fixed query disappears. We cannot take advantage of the fixed query. We don't know that.
no, because I'm still comparing both algorithms on only one query and just growing the right. So as a function of the number of cards in your deck, this here will require exponential time, while the nested for loop I showed you would be polynomial time. So it's really data complexity in both cases. Yeah.
So the same. The problem is the same.
You're fixing the formula on both sides. I see.
Yeah. All right.
Yeah, it's perfect.
So here are some more results. So this is what we know about this first order model counting problem.
Go on.
Thank you. So this is everything that Dan told you this morning. There exists this class of safe queries, safe UCQ queries, and they have also their analog as safe CNF queries. And for these queries, Dan's algorithm can solve all of them efficiently, right? At least for the UCQ ones. And then this is what Dan Olteanu told you about this morning. It says that, so he has a different name for this, a slightly different characterization, but you can extend this with negation, and still the probabilistic database algorithms can solve many of these problems. But there's more. So one of the key results specifically for this first order model counting problem is that every sentence in FO2, every CNF in FO2 can also be counted efficiently. So FO2 means that you have a CNF with clauses, and every clause has at most 2 logical variables, 2 quantifiers. And actually, it doesn't really matter what the quantifiers are. Any sentence in FO2 can also be, the models can also be counted in polynomial time. Yeah?
This is over symmetric structures.
Yeah, so this is over symmetric structure, symmetric weights. And then we also showed that gamma acyclic conjunctive queries can also be done efficiently. So these are all of the new results you get when you have this very symmetric setting. So here are some interesting observations. This is the hard query that both of the Dans talked about. So this is actually sharply hard to compute on a probabilistic database, but counting its models is also polynomial time in the size of the domain. You may wonder, what if I have a sentence with 3 logical variables? What if I have a CNF with 3 logical variables in the clauses? Well, the cards example is one of them. So some of them clearly are also efficient to compute the model count of. This one here, that's 4. Okay, so that one is not in there. This one is also efficient, by the way, right? There are also hard ones. So we know that not all of the CNFs with 3 logical variables are efficient to compute the model count of. Why? Because you can actually construct a sentence that counts accepting computations of a Turing machine. So you can construct a sentence that's what's called Sharpie1 complete. So it's solving all problems in Sharpie with the unary input. And we show that this sentence, you can actually write it with only 3 logical variables. So there exists this sentence here that probably we can never do this lifted inference for efficiently. There also exists a conjunctive query that is Sharpie1 hard. Right? So I won't go into the complexity details here, but we can talk about it afterwards.
That's my question. So safe type 1 CNFs, they're not a superset of safe monotone CNFs because it's only for Reed-Wants formulas. Isn't this correct? When you say the safe type 1 CNFs that Dan Olteanu showed today, it looks like it's a superset of the safe monotone CNFs, but it's only for the hierarchical case, right?
So these are ones that have negation. These don't have negation.
Right.
So it's definitely a superset.
Yeah. They're overlapping, but they
Oh yeah, so they might overlap. Yeah, so depending on how you define it, you can. Yeah. So this one, this one means just add negation and some things stay efficient. Let's keep it at that level. Okay, so a bunch of things are hard, but then a lot of very simple queries we just have no clue. So here's a very simple one with 3 logical variables. It says that the friends relation is a transitive relation. Super easy sentence, super easy to ask mathematically how many transitive relations are there over a social network of n people, a graph of n people, and no one knows how to count this efficiently, as far as I know. So if you go and look up in the combinatorial enumeration literature, people have these recursion formulas, but no one really knows how to do it efficiently in time polynomial in the size of the graph. Right? So this is a very simple problem that we really don't know the complexity of for model counting.
When was it? Late 60s, like Lepsky et al. Of 0-1 law. And they're starting by counting models. That's exactly what they're doing for the symmetric case.
Yeah, so we have an anecdote about this towards the end, yeah, if I get there. So for the machine learners, I have a cartoon version of this result, which says that FO2 is liftable. It doesn't matter what you want to express. Colleagues of the same age are more likely to be friends. Any kind of correlation you want to express between pairs of entities, and it doesn't matter how many you've got, you can always compute a partition function of your Markov random field in time polynomial in the number of people. So that's the machine learning version of this result. All right. So what is this really good for? I gave you this motivation in the beginning, and how does it match? How do we use this for that? So remember, we'd like to ask, does there exist this co-author? And this is what we'd like to get. But I would like to argue that the way that we currently do query evaluation in probabilistic databases does not exactly fit reality in many ways, but at least in this way, in that these tuples, we don't have all of them available. For instance, it's very possible that NEL or Deep Dive or your favorite probabilistic database system, that it's missing this one fact that Erdős and Strauss are co-authors with some probability, right? And this means, according to the closed world assumption, that this query here has 0 probability, because Einstein has co-authors, but none of those people are co-authors of Erdős, so this thing has 0 probability. All right? This thing also has 0 probability that Bieber and Erdős share a co-author, that Einstein and Erdős share the specific co-author Strauss, 0 probability, that Bieber and Erdős, that Bieber is that person, and also that Einstein and Bieber wrote a paper and simultaneously did not write a paper together. So all of these queries all have probability 0. And intuitively, of course, this doesn't really make sense to assign 0 to all of these probabilities. To all of these queries. Intuitively, we know, for instance, that this query should have a higher probability than these guys, because this is a more general question, right? These ones entail this one, right? We also know that they should have a higher probability than this query, because actually this should always have 0 probability, no matter what your probabilistic database is, because it's unsatisfiable. And then there's also some more vague sense of relative probability, which says that these two queries, logically speaking, they're incomparable, but we have all of this evidence that Einstein wrote papers with all of these people, and we have no evidence that Bieber wrote any papers. So intuitively, this probability should also be higher than this one, even though both of them cannot be proved in any way with the tuples that we have available. All right? So that's a problem. So here's another problem with the current way that people use probabilistic databases for these knowledge graphs. If you're a machine learner, you're familiar with this Bayesian learning loop. You have some prior belief about these guys being co-authors. You observe a web page, you read some text, and your machine learning algorithm conditions your distribution on this information and then changes your belief. You observe another page, your belief changes. It's a very nice, principled, and sound way of reasoning in machine learning. All right? But this is not exactly what's going on in knowledge graphs. So in knowledge graphs, what goes on is that first your database is empty. This tuple is not in your database. It has probability 0. Then you'll read a web page. You find some text here, and this evidence makes you change your belief to be 20% probability, and so on. And it looks innocuous, but what's really going on here is that this is absolute mathematical nonsense, as far as I understand, that you can never have a belief that something is probability 0, condition your distribution on an event, and then get a non-zero probability out of it. Right? So mathematically, this whole learning loop that people use in knowledge-based completion, at least when it's based on the closed world assumption, is completely broken from a principled mathematical point of view. So also, this is something I don't really like, even though it works in practice, of course. Here's another problem. Reality is worse. If you look at these knowledge bases, and look at the probabilities of the tuples in there, they're almost all very close to 100%. Why? Because these things read the web constantly, and they're extracting all of these tuples, and most of them are very unlikely, and they just go to the garbage. Right? So only the most likely tuples are kept, which means that we know that there's a whole bunch of tuples here that we don't, that we intentionally threw out. And you may wonder, yeah, okay, this is a temporary issue. At some point we will have found all of the tuples. And I want to also show you that this is not the case. If you just have a binary relation at the size of Facebook, so a couple billion people, then to have a probability, a real Bayesian belief about every pair of people being siblings, you need already 200 exabytes of data. And how much is this? Well, all of Google's storage is only a couple exabytes, which is this many punch cards above the city of Boston. So 200 exabytes for one table is really, really a lot of data. And I don't think we can ever assume that we will complete these knowledge bases and that the closed world assumption will at any point in time start to hold. Right? Okay, so here's a very simple solution. It's definitely not the perfect one, but it's, let's say, going in the right direction. So we already saw that these knowledge bases, they throw out all the tuples that are less than, let's say, 70% probability. Okay, so let's assume that everything that's not in our database has a probability between 0 and 70%. We just don't know what it is. Right? So this is a very close match to how these systems are used in practice. And what we then can do is ask, what is the probability of my query for any kind of choice of probability for the tuples that are missing. And now we cannot compute one probability anymore, but we can compute lower and upper bound. So for instance, here, this probability of the query 2, we know that it's larger than or equal to 0, because if we don't add any tuples to our database, if they all happen to have probability 0, that's the probability we're getting for this query here. Right? But now I also can say that it's possible to add this one tuple to our database with probability lambda, which is our threshold. And if I do so, then my probability becomes 0.7 times lambda. And this is the maximum probability I can ever get for my query by completing the database. So in this open world probabilistic database work, what we propose is these semantics, a very simple extension of the existing ones. And I think it makes sense. How do we compute these things? Well, the lower bound probability for UCQs is just the probability of the query on the database without adding tuples. This is our closed world probability, and Dan knows how to compute this very efficiently, right? The upper bound is also easy to compute in the sense that we can add all of our tuples lambda to the database and then compute the probability of our query. And this gives us an upper bound because of UCQ being a monotone sentence.
You mean all tuples? You mean all these 200 exabytes?
Yeah. So yes, this is polynomial time if from a complexity point of view, but you get your quadratic blowup and you basically built this 200 exabyte data set. Right? So this is not really a practical solution, even though complexity-wise it looks fine. So let me give you a rough intuition of how you can do better. Let's look at a specific query and how the probabilistic database system would compute it. So here it would look at every individual person X and solve the problem independently for all of these X's and then combine them in this way. Right? This is the inference rule that Dan showed you this morning. And the complexity is polynomial time. If you do this, you have to do this recursively, so you end up looping over all of the people in your domain recursively. Now, a key observation is that a lot of these subqueries here, they have no supporting facts in the database because, for instance, D is not a scientist and has no co-authors. So a lot of these things actually have no support in the database, which means that they have probability 0 in the closed world, which means that you can just ignore all of these. And there is a way to implement the probabilistic database algorithm to actually have complexity that is linear in the size of your database instead of being polynomial, by being clever about not looking at parts of your database that are useless to you. So that's nice. Actually, the dichotomy of Dan is not between Sharpie and P time, but it's between Sharpie and linear time. Now this goes wrong if you have an open world setting, because now these things, even though they have no support in the database, they still have some probability. But the nice thing is that, and then you get into your 200 exabyte problem. Now the nice thing is that all of these queries that have no support in the database, they all have the same probability, so you can compute all of them together with this one expression. So here's where I tie the motivation I have for open world probabilistic database query evaluation to this first order model counting problem. Computing the probability of all of these guys over an empty database, that's exactly the weighted first order model counting problem. So all of the algorithms that I talked earlier about allow you to do this efficiently without getting this extra cost. And this also means that if you do this well, you again get linear time complexity. So here's the overview. Dan Suchu's dichotomy is between polynomial time and let's call it PP now instead of Sharpie. If you implement it nicely, you can make it a dichotomy between PP and linear time. And surprisingly, for open world probabilistic databases where you have a polynomially larger number of variables, you can still compute all of these linear time queries in linear time in the size of your closed world database. So you don't run into this 200 exabyte problem. You just, again, do just one pass over your data. And of course, the PP queries, they stay PP hard. We also look at queries with negation, where linear time queries can either stay linear or become as hard as NP complete. And some of the PP queries on the open worlds, they stay PP hard, and others become NP to the PP complete. So there's a lot of complexity stuff that you can study in this context. Here's another. So this kind of wraps up the query evaluation motivation for first order model counting. It's open world query evaluation. Here's the other motivation, which comes from the statistical relational learning community, which is that if I want to, for instance, learn the parameters of my Markov logic networks, I have to learn these weights here. To learn these weights, I have to compute the partial derivatives of the likelihood with respect to these weights, which ends up being a count in your database, very efficient. You just count how often is this sentence true in my database. And then here you count the expected number of times you expect this sentence to be true in a random database. And this requires inference. This requires that you compute your partition function of your Markov logic network. And also no surprise, this problem is also simply first order model counting. And if you now plug first order model counting into your parameter learning algorithm, what you get is, for instance, this behavior where we change the domain size of the number of people in our MLN. And with 30,000 people, we learn the parameters of our MLN in 12 seconds. And it doesn't maybe look expressive, 30,000 people. But if you look at the Markov network that's actually learned here, it has 900 million random variables. So these are really, really very large, very densely connected graphical models. And computing their partition functions is really efficient.
It sounds especially close to the amount of money that Trump lost in 1995.
Yeah, I made up this number. No, it's this squared plus the same number. Yeah, I didn't make it up. If you would run variable elimination, it would look like this. It would just go up here for like 10 people. It would start to break. Right. All right. You can do the same thing with structure learning. You can use structure learning of these liftable models, and you get much, much better likelihoods for your statistical relational learning algorithms. So let's leave it at that. I think I have like 1 minute left. 1 minute for the broad picture for all of the other questions that may arise. This is a very general framework. You have logic with weights. You can apply this to other types of logics, obviously. You can use the semantics of logic with weight functions to do probabilistic reasoning. It's kind of like an automatic way to do probabilistic reasoning in different contexts. For instance, some work that we try to do is on using SMT, so another first order theory with linear inequalities, and compute the volume of your SMT theory with respect to a weight function, where we try to use the algorithms by Moshe and by Bartz and other people based on universal hashing. I wouldn't say that we solved this problem, but at least it's a direction that I think is interesting and promising. Another direction is probabilistic programming. What if your logic is a logic program or a data log program? Now you can ask, what are the models of my data log program with a bunch of weights for all of my tuples in the database, and compute, for instance, probabilities here for the network reliability problem or any kind of data log query you have. So for the functional programming people, this looks like logic, but it's really a probabilistic program that tries to find a path in a graph. So if you're more into functional probabilistic programming, all of these logic-based techniques, they also apply to your discrete functional probabilistic programming languages in a very nice way. Knowledge compilation, Dan talked about it. There's also a first-order circuit language that expresses these computations. So it's kind of a declarative way of specifying the model counting, and it can be done also in polynomial time. If you're into MCMC, these ideas, you can also just take them to your favorite MCMC algorithm and exploit the symmetries by mapping, in your Markov chain, mapping a given state to one of the approximately symmetric states and kind of exploit the same exchangeability and symmetry that you exploit when you do this model counting inside of an MCMC algorithm. Yesterday, there was a very interesting talk on exchangeability that I watched on YouTube because I wasn't here. So there, I think exchangeability is used to characterize what's computable, and in this work, exchangeability is used to characterize what is efficiently computable in polynomial time. So there's some connection there that I don't understand, but I think is interesting. So for instance, all of the whole tractability of FO2 can be characterized as a specific form of partial exchangeability with a specific type of statistic. So there's a connection there. That I don't have time to talk about. 0-1 loss, I had a slide about it. So all of these theoretical results are tied to the spectrum problem. You can also study the combined complexity of first order model counting, which happens to be NP complete for FO2, NP space complete for FO in general. 0-1 loss are obviously related as the limit of your first order model counts. So all of these things I don't have time to talk about. So this is the conclusion. I think relational probabilistic reasoning is very interesting because it combines all of us here. And you cannot argue with the need for relational models, probability, statistical machine learning, and also scalability. For specifically the open world data model, I think it makes sense because it matches what people use in practice, how they use their knowledge graphs. You get free open world query evaluation for UCQs, but if you have negation in your query, it gets very expensive. And then finally, this is kind of the history of probabilistic reasoning in AI, at least. Conditional independence speeds up your inference exponentially. Contextual independence, local structure, set solving techniques speed up your probabilistic reasoning exponentially. And then I hope by the end of the decade, we'll all agree that symmetry exchangeability does the same for you. And I think multiple people are looking at that direction as a property. So thank you.
So I think if you look at Fagin theorem, I don't think you'll find a good connection there because Fagin used beautifully elegant model theoretic techniques, but it goes away completely from the counting aspect of it.
Yeah. So Fagin actually emailed us. Yeah.
Earlier result by Levsky, Galakanov. I mean the so-called four Russian, three Jews and a Russian. And they actually go by very, very, very painstaking counting argument. Then they take the expression that they get, and they take them and see what happens asymptotically, and they show that this expression go to 0 or 1.
Oh, nice.
First, they do. It's a very, very difficult. I mean, we spent a month reading that paper.
I thought it was only in Russian. No?
It was estimates, because it was bounds, and that's why. What they got out of this is that the probabilities converge asymptotically exponentially fast. But they combined to quantify elimination with counting, like Fagin.
Yeah, but
it was still the bound of the extension axioms ultimately. It was not exact counting.
It's much closer. Fagin does no counting essentially.
He does.
So Fagin tried to do this.
Other than just the extension axioms, but not for a specific
the bounding.
Not for a specific graph. That's the paper I would look at.
So when we did this work on Sharpie1, actually Fagin emailed us saying, "Oh, it's really great because when I tried to prove the 0-1 law, instead of doing the proof that I used, I actually tried to show that the limit of the model count of my sentence would approach 0 or 1, and I worked on it for 6 months and I couldn't solve it." And he says, "And now you proved that actually what I was trying to do is Sharpie1 complete. So you proved that my initial approach could never have worked." So he emailed us about this. Right, Dan? Is that correct? Yeah.
So a couple questions. One is, so you're adding in the open database, the solution where you add lambda everywhere. So this probabilistic database, or I understand this is being generated from the MLN. Is that right?
It could be.
Yeah.
So in the open world probabilistic database setting, I just assume there is a probabilistic database that comes from NEL or Deep Dive or Google Knowledge Vault or Google Knowledge Graph that is just tuples extracted with statistical machine learning from text, right? So that's the motivation there. The MLN reduction is the motivation for the other side of things, for the statistical relational learning side, where so these are actually different things. Yeah.
And I made one more comment, which is so on the mathematical nonsense, moving from zero probability to then conditioning on something and being non-negative. So that is nonsense if you assume that you're working with sigma additive probability measures, but if you work with merely finitely additive ones, then it's possible for such things.
So I should weaken my statement there. Yeah.
It's a very strong weakening, but and I don't. There's very few people alive who would bother to finally additive probability. But,
it's good to know, yeah.
So, I think I don't know if it was your papers or Niepitz's papers, or maybe one of the ones you both wrote together. You give an example that you get a lot of speed up on, I think it's a smoker problem with 200 smokers or something like that. But as soon as you have evidence on 3 of the smokers, then it's slower than just grounding the whole thing.
Mm-hmm.
So in the real world, we sometimes have evidence.
Yes.
That's a bit of a problem.
Yes, so for this partition function computation in learning, the reason why it works is because you don't have evidence and you have all of the symmetries. Of course, if you want to do prediction, then you condition on a social network on a bunch of data, and all of the symmetries in your graphical model are gone. And in the original work on exploiting symmetries in MCMC, this would only work if you had exact symmetries. In this paper that I did together with Matthias Niepert, we said even though there is evidence, and everything is asymmetric, you can actually very easily find approximate symmetries. For instance, on the web graph, IBM and Google and Facebook are approximately symmetric. So you can use this as a proposal distribution to jump between approximately symmetric states. And all of these lifted MCMC algorithms, they start to work in this context where you have evidence and where you have asymmetry. So that problem has actually been kind of solved with proposal distributions instead of exact symmetries.
I'd like to tell a story about Ernst Strauss because I might never get a chance to tell it again. When I was a student here in Berkeley in the mid-50s, he came to visit. He's a number theorist. He was a number theorist and a very close friend of Erdős. And now Erdős traveled around the world and would appear on people's doorsteps for extended periods as house guests. That's how he got to write so many joint papers with people. They would work on something and then the friend would have to write up the paper. Strauss told us that Erdős came one year and all of a sudden he told him, I want to learn to drive an automobile. So very reluctantly Strauss agreed to give him a lesson to drive the automobile. When they got in the car and Erdős was behind the wheel, he said, now let's see what happens when you turn the thing this way. Now let's see what happens when you turn the wheel that way. So one lesson was enough for Erdős to give there. Many years later, I was at a conference where Erdős was giving a talk. Completely off the top of his head, he took overhead projector slides and he would say, now let's see what happens when you take this series. Now let's see what happens when you take that series. So I realized he did his mathematics in the same experimental way that he tried to learn to drive.
Since we are telling stories about